So this lesson is on the derivative of trigonometric functions. You can see from our first pattern, the derivative of sine, so if the function is sine x, the derivative, f prime of x, is just cos x. So it's a pretty simple derivative to take. And if you're wondering why that's the case, maybe this is what you can do for yourself. Take a blank piece of paper, sketch out a sine curve, and then think about what happens to the slope, where the slope is equal to 0, where the slope starts. And if you piece that together, you should see that you get a cos curve for the slope of the tangent. Anyways, let's do the first example. Y equals 2 sine x. Well, if the derivative of sine x is just cos x, it's pretty straightforward to find the derivative of this. Recall how if we have a constant in front, when we take the derivative, we can just leave that constant sort of outside of the derivative and then take the derivative of the rest. And the derivative of sine x is just cos x. So this derivative really just equals 2 cos x. You don't really have to show that second in between step. You'll notice that part B is actually exactly the same question. So I'm going to change it a little bit to make it a little more interesting. What if I make this the derivative of 2 sine x squared? Now what do we do? Well, if you think about it, think about all the previous examples that we've done, like taking the derivative of exponentials. When we have a function within a function, in this case sine x is a function and x squared is the function inside, we always have to use the chain rule. So recall how we can, if we wanted to use the chain rule here, we can call u equal to x squared, and then we would do du by dx is just 2x. And then if we wanted to change this, this would look like 2 sine u, right? We can take the derivative of that because it only has one variable in it, and the derivative of this, I'm going to call this dy by du, is equal to 2 cos x. It's the same as the previous question, or in this case cos u, right? So to find the derivative of the whole thing, dy by dx, we have to multiply dy by du, which is this, by du by dx, which is this. So what we end up getting is dy by dx is just equal to 2 cos, instead of u, I'm going to put back the x squared, and then times 2x. Notice how this is the same as all our previous patterns, right? Where if we want to take the derivative of a function within a function, we take the derivative of the outside function, right, which in this case was sine x, and we change that, leaving what's inside what it was, right? And then we multiply by the derivative of what was inside, which in this case is just 2x. So there's our answer. Of course, we could simplify that as 4x cos x squared, but I'm okay with not simplifying in this case. Here's one where it's the same idea. So I'm going to use the chain rule without actually showing the work for the chain rule here, but g prime of x, again that 5 doesn't matter, it's not included in the derivative because it's just a constant, so we can leave that out. We're going to have the derivative of a sine, we know that is cos. And then we have to keep what's inside the brackets the same, but then we have to multiply by the derivative of what's inside, which in this case is 2x. So there you go, that's the answer, using the chain rule without showing the work, and yeah, similar to the previous example. The derivative of cosine, not much more difficult, it's just negative sine x. Again, if you want to see where this comes from, just sketch for yourself a cos curve, and then think about how that's related to negative sine x. So anyways, let's take a derivative of this first one. Y prime equals 8, that doesn't get involved, and then cos x is just going to become negative sine x. There it is. And if we wanted to simplify a little bit, just to make it look a little bit nicer, negative 8 sine x. That one I do like to simplify because that negative sign sort of looks like minus there, so just to be a little bit less confusing, I'm just going to stick the negative out in front. Okay, here we go, a little bit more challenging. So this one has inside the cos 1 over x. So to make it a little bit simpler for us, before taking the derivative, I'm just going to simplify that as x to the negative 1. Okay? So now let's take the derivative of that. F prime of x. Well, again, we have to use our chain rule here, right? So think about the thing that's inside the brackets as being u. So when you take the derivative of cos, which ends up being negative sine of u, which in this case is just x to the negative 1, times the derivative of what was inside. And the derivative of x to the negative 1 is negative x, and then we decrease it by 1 to the negative 2. If we wanted to write that with positive exponents, we can go back and do sine of 1 over x times negative 1 over x squared. And there is our derivative. This one again, the notation is a little bit silly here. What cos squared x actually means, I'm just going to rewrite this out in a less confusing way. What this actually means is cos x all squared. That's what that cos squared x means. The squared in the middle just makes it a little bit confusing, so I always like to rewrite it like this. And in this case, it's sort of like a power of a function rule, right? When we take the derivative, we're going to bring that 2 down in front, and then it's what's on the inside, and then we decrease that by 1. But we also got to remember we got to multiply by the derivative of what's on the inside for the power of a function rule, and in this case, the derivative of cos x is just negative sine x. There we go. There's the answer. Of course, you could write that a little bit simpler. Again, before I said I like to bring the negative out in front. Negative 2 cos x sine x. There we go. That's it. So when we're taking the derivative of tangent, it's a little bit more tricky. The derivative of tan actually ends up being secant squared x, which is a little bit strange. We're not going to cover the proof of why that is here, but if you're interested, go look it up for yourself. Recall what secant actually means. Secant is just 1 over cosine, right? So secant squared x is basically saying the derivative of tan is 1 over cosine x squared. That's basically what we're saying. We like to write it as secant because it ends up being a little bit simpler. We don't have to work with the fact that's in the denominator. So let's try the first one here, y equals negative 4 tan x. Well, the derivative of this, again, there's a constant out in front, so we can just leave that out in front, and the derivative of tan x is just going to be secant squared x. That is our derivative. Oh, sorry, y prime is equal to that, right? Okay, b. Obviously, b doesn't have tangent in it, so I'm just going to change that. That's a mistake. This should just be tan. So the derivative of this, again, think about our chain rule. If we make 1 over xu, it's actually the same as the previous one, right? So I'm just going to write this as x to the negative 1, right? Just like the one that's right above it for cosine. And in this case, we use chain rule, so u is equal to x to the negative 1. So when I take the derivative of this, it's the derivative of the tan part of it, what ends up being secant squared x to the negative 1 times the derivative of what's in the brackets, which the derivative of x to the negative 1 is just, again, negative 1 times x to the negative 2. And then rewriting that with positive exponents, the answer is secant, oh, sorry, this should be f prime x. Missed that. This should be secant squared 1 over x times negative 1 over x squared. Okay, that's it. Okay, now this one's a little bit trickier. It looks confusing. Remember what the tan squared t squared plus 4 means. That just means the whole thing is squared. So I'm just going to rewrite this first as tan t squared plus 4, and this whole thing is squared. So we know we can sort of use power of a function here, right? So let's use our power of a function. We know we can bring down that 2 and write whatever's in the brackets without taking the derivative. And then what we have to do is we have to multiply, and then the exponent obviously becomes a 1 here, so it doesn't matter. We have to multiply this by the derivative of what's inside the bracket. So the derivative of tan t squared plus 4. A little bit tricky. Well, we know the derivative of tan is just secant squared whatever's in the brackets. And then we have to multiply by the derivative of that, which in this case is just 2t. So there's our derivative. A little bit complicated. It's sort of like you had to do chain rule twice, right? One as the power of a function rule here to bring this 2 down in front, and then we have the regular function there multiplied by the derivative of what's in the bracket. So just to illustrate here, this is the derivative of what's in the brackets here, right? So if you're confused by that, what I would recommend, try this question again, but call u that part in the brackets, tan t squared plus 4. Barely fit it in there. Yeah, tan t squared plus 4. And then try it yourself, and you'll see how that works out. Here we're asked to find the derivative of these secondary trigonometric ratios. And the way to do that, we don't want to memorize more things for taking the derivative of cosecant, secant, and tangent. So what we can do instead, let's just transform this. Remember what cosecant is. It's really just 1 over sine. So can we take the derivative of that? Well, I'm going to write this in one more form as sine x to the negative 1. Can we take the derivative of that? Yeah, it's just using chain rule or power of a function rule, right? We bring down that negative 1, and then we have to multiply by the derivative of what's in the brackets, right? So y prime is just going to equal, bring down that negative 1, negative sine x to the power of negative 2. So all we've done is the derivative of the outside function times the derivative of what's inside, sine x. And we know the derivative of sine x is just cos x. If we want to write that with positive exponents, we can write negative cos x over sine squared x. Right? Because that sine x is just squared, so we can write it as sine squared x instead, if you like. So we can do the same thing with secant. Remember, secant is just 1 over cosine. So it's like secant x is just cosine x to the negative 1. And we can take the derivative of that in the same way we did previously. So y prime equals, using the power of a function rule again, negative cos x to the negative 2 times the derivative of cos x is negative sine x. And there we go, just to simplify a little bit, make that a positive exponent. Those two negatives are going to cancel out, so we just end up with sine x over cos squared x. That's it. And lastly, the derivative of cotangent x. We know we can rewrite cotangent as tan x to the negative 1, right? 1 over tan x. And then we can take the derivative of this using the power of a function. Y prime equals negative tan x to the negative 2 times the derivative of tan x, which we know as secant squared x. Simplifying a little bit, we get that it equals negative secant squared x over tan squared x. So, do you need to memorize new things to find the derivative of cosecant, secant, and cotangent? No, just turn it into sine, cosine, and tangent, and then take the derivative of those. Easy. How can we take the derivative of this? In this case, I'm going to use the chain rule here. Remember, when we use a chain rule, we have to get rid of all the x's in the equation. So it's not like I can make u equal to cos x or u equal to sine x, but what I can do is I can make u equal to sine x cos x, right? And then when I plug that back in here as u, y is just the square root of u. So we can take the derivative of both of these functions separately. dy by du is just going to be, remember u is just, let me actually rewrite that as u to the 1/2. So this looks like 1/2 u to the negative 1/2. And then du by dx is, how do we take the derivative of sine x cos x? What do we have to use? Well, the key is we're multiplying sine x by cos x. So what should pop into your mind is that we should use the product rule. And the product rule tells us I'm just going to write it out here. So if we call this f, we call this first part f, and we call this second part g, right? The derivative is going to be f prime g plus fg prime. So du by dx is going to be the derivative of f, so the derivative of sine x, which is just cos x, times g, which is cos x as well, plus f, which is sine x, times the derivative of cos x, which we know is negative sine x. Sorry about that squishiness on the side. That says negative sine x. So we can simplify this a little bit, that du by dx is actually equal to cos squared x minus sine squared x. And then when we find the derivative du by dx, or sorry, dy by dx, we're just multiplying this derivative by this derivative, right? That's what our chain rule says. So I'm going to convert that u back into sine x and cos x. And I'm going to put also this, actually let me do this first. I'm going to put this 1 over 2 root u, just to put that in the denominator, make all the exponents positive. So just multiply 1 over 2 root, and instead of u, I'm going to substitute it back in as sine x cos x, times what we got is the derivative of du by dx, which is just cos squared x minus sine squared x. That is a minus sign, and that should be a square bracket there. Okay, so there is our answer. So this last one, you should be able to try yourself. So give it a shot now, and then I'm going to go through one way of finding the answer. So there's actually multiple ways of finding the answer here. I'm just going to go through what I think is the most straightforward way, and that's just by using the chain rule here. So I'm going to call u equal to cos x squared, because we know how to take the derivative of that, and we should be okay here. And in that case, f of x just becomes, oh sorry, that's wrong, it should be f of u. F of u equals tan u, right? So taking the derivative of these, f prime of u, or du by dx, or sorry, dy by du, is equal to tan u, which is just secant squared u, and du by dx, or u prime, is going to be the derivative of this, and the derivative of this is, well, we're just using our chain rule again. We know the derivative of cos is going to be negative sine, and then we have to do that, just keep it the same, times the derivative of what's inside, which is 2x. Think back to our previous page here. And then to find the derivative of the whole thing, we just need to multiply the derivative of the function, or of y, by du by dx, right? So our final answer comes out to be f prime of x is equal to secant squared, and I'm just going to plug that back in, cos x squared, times negative sine x squared times 2x. And that is our final answer.